Good afternoon.
Hello, Mr. Islam.
Hi, how are you?
I'm good, thank you. What about you?
So, um, how it's going? How it's going about your study?
Like overall,
Yes, overall. Is
well,
there
I think
any improvement process?
improvements. I have some difficulties in algorithmization
Mm-hmm.
with I don't know. I think you know this for nested for loops.
Mm-hmm.
Yeah, so I have like a little problems with that, but overall, I think it's pretty good.
Okay. Okay. Please write the message to other students in order to join today's class. And after the 5 minutes, we will start today's lecture. Okay.
Okay.
Okay, since we waited 5 minutes and I think I have observed that no one else joined today's class. Okay, let's start today's class. And by the way, I'm taking the attendance. Vladimir, Kamla, could you hear me?
Yes, yes.
So I'm taking attendance. So this attendance is recorded in our system. So tomorrow it will influence on your mark also. Therefore, please keep note and please send this message and information to other students. Okay.
Okay. Tomorrow, you mean it will affect the mark of our midterm exam?
Now the mark of the midterm exam I will not.
Oh, you
Uh,
mean the total grade, the mark, total mark, right?
sorry, I couldn't catch you. What do you mean?
You said that it will affect something. What will it affect?
Effect for your mark in total mark. I said.
Total mark. Yeah, that was what I asked. Okay,
It will
I
not
got it.
influence on your midterm exam. I think it will also consider it in your total marks.
Okay.
So today is 21st of the November 2020. So in my class, you, Vladimir Samoilov and Kamran.
You said tomorrow you will like send the attendance of the lectures, the all the lectures till today, or
No,
you said yeah.
by the rule, we have to conduct the attendance in every lesson, but I couldn't make it. I did it once, but in other classes I couldn't because I forgot about it. Now I have to take attendance for myself and for the administration also because you like no one else, at least four students has to attend to the class. Okay.
Okay, I'm writing to the group right now.
We
Just waiting
have
for it.
to give the how to say the honest improvement, honest process of the students' performance, attendance, and evaluation to the Riga Technical University. Okay, let's start today's lecture. Introduction to computer architecture. Okay, our plan. Now, our topic for today is the memory. Like we will talk about the cache. So our plan for today is basic concept and cache memory. So before talking about the cache memory, cache, like I have to display you the overview picture. So you see in the memory, we have main memory, we have central processing unit, and we have input output system. Yes. So in CPU, we have cache memory. This cache memory is helps us to execute multiple instruction beforehand. I will explain you in detail, okay? But cache memory is situated near the memory in order to help the terminate the process fastly. So before setting about the cache memory, let me explain you the basic fundamental knowledge. So the maximum size of the memory which is used in any computer is determined by the addressing scheme. So in order to know the maximum size of the memory, you have to look the addressing scheme. So for example, if 16-bit computer that generates 16-bit addresses is capable of addressing up to 216, it means that it is equal to 64 kilo. memory location. Same, F machines whose instruction generates 32-bit addresses, it means that it's 2 power of 32. Utilize the memory that can up to 232, which is 4G memory location. So in 16-bit addresses, it's 64 kilo memory location. In 32-bit addresses, it's 4G memory. 4G means 4 gigabyte. So for most modern computers are byte addressable. From the system standpoint, we can view the memory units as block box. So data transfer between the memory and processor takes place through the use of two processor registers, MR and MDR. So MR is memory address register, MDR is memory direction register. So look at the picture, and in this picture we have connection of the memory to the processor. So look at the processor. Processor consists of two components, MR and MDR. MR connects and sends its addresses to the memory, and memory sends its answers, its results to the MDR. So we have control lines which consist LW and MVC. So it helps to keep the connection between the processor and memory. So up to uh, two power key. Key means 1000. Kilo means 1000. Two power 1000 addressable location we have in the memory, and word length, which is equal to n bits. So in order to measure the speed of the memory, is the time that elapses between the initiation of operation and completion of that operation. So initiation means beginning of the operation, and the finishing of that operation is equal to speed of the memory. So this is referred to memory access time. So when you uh, want to measure the speed of the memory, actually memory access time, so you have to measure between the initiation of the operation and completion of the operation. And also important measure as the memory cycle time, which is minimum time delay required between the initiation of two successive memory operations. So, we have two, sometimes we face the two, like memory operation, which is started at the same time, with it, which starts and begins at the same time. But we have some time delay, which is also considered as important measure of the memory cycle time. So memory unit is called random access memory. If any location can be accessed for read or write operation in some fixed amount of time that is independent of the location address. Okay, so the memory cycle time is bottleneck in the system. So let me explain you what is bottleneck. So I will write to the, let me write in chat session. So bottleneck means in Russian language, I wrote in the chat session, the translation.
Okay.
So then we have one way to reduce the memory access time is to use cache memory. Cache memory is a small, fast memory that is inserted between the larger, smaller main memory and the processor. So virtual memory is used to increase the apparent size of the physical memory. Also, data are addressed in virtual address space that can be as large as addressing capability of the processor. But at any given time, only the active portion part of this space is used to map onto location in the physical memory. So other part mapped onto the bulk storage devices, for example, in magnetic disk. So let's talk about bandwidth. So do you know about bandwidth?
No, never heard about it.
So in order to transfer a block of data, it's of interest to know how much time is needed to transfer entire block. Since blocks can be variable in size, can be differentiable in size. Yes, block can be small, block can be large. We have different type of the block in terms of the size. It is useful to define. Define means um, to analyze performance measure in terms of the number of bits or bytes that can be transferred in 1 second. So this measure is often referred to as the memory bandwidth. So when you want to analyze performance measure in terms of the number of the bits, so or bytes that can be transferred in 1 second. So bits and bytes that can be transferred in 1 second, it means that it's bandwidth. Okay, the bandwidth of the memory unit depends on the speed of the access to the stored data and on the number of bits. So in short, like a bandwidth is number of bits or bytes for per second. Okay.
Okay.
So let's talk about cache memory. So the speed of the main memory is very low in comparison with the speed of the modern processor. Hence, it's important to devise a scheme that reduces the time needed to access the necessary information. Since the speed of main memory units is limited by electronic and packaging constraints, the solution must be sought in different architectural arrangement. So efficient solution is to use fast cache memory, which is essential makes the main memory appear to the processor to be faster than it really is. So effectiveness of cache memory. So before talking about the cache memory into deep, let me show you one short video about the cache memory so that you can understand the concept more deeply. Okay. So if you
Okay.
have problem with the voice, let me know and I will fix the voice as soon as possible. Okay.
Okay.
Students, coming to the next topic, that is a cache memory. In the previous video I explained about the students coming to the next topic, that is a cache memory. In the previous video, I explained about the main memory. So in the memory organization, I'll explain memory hierarchy and the main memory. Now let us see the next hierarchy, that is a cache memory. So what is the use of this cache memory? It is a memory it is the memory which is very nearest to which is very nearest to the CPU. So the cache memory is the memory which is very nearest to the CPU, and all recent instructions are stored in cache memory. Stored into cache memory. So the cache memory is present within the processor. So not within the processor. After the within the processor, you are having the register. So register is very fast when compared to the cache. So first, this is the CPU. So CPU, or in the CPU, you are having the registers. So after that, you are having the cache memory. After that, you are having the main memory. So this is a hierarchy. So the data what are the files that you are open, that will be stored in the main memory, and whatever the program that has to be executed, that will be sent to the cache. So the cache will send bit by bit to the register, and the register will send to ALU to perform the operation. So the cache memory, this cache memory is very nearest to the CPU. So which is very nearest to the CPU, and all recent instructions are stored into the cache. So whatever the recent instructions that the CPU has to be performed, those instructions will be taken from main memory and stored it in the cache. So one by one, the cache will send that information to the registers, and from registers, the ALU will take that instructions and performs the operation. So this is the cache memory. A cache memory is attached for storing. A cache memory is attached for storing the inputs which is given by the user. So the cache memory is attached for storing the inputs which is given by the user, and which is necessary for the CPU to perform a task. So that is the operation that can perform by the cache memory. So cache memory lies in between the path between the processor and the main memory. So it has less access time when compared than memory, and it is faster than main memory. Okay. So the cache memory implements the cache logic, and also if processor finds the address code or data is not available. Suppose, let me write that. Suppose if processor wants to get some data from the cache. If processor finds the address code, it finds some address code data is not available in cache. Suppose whatever the data that the processor wants, that data is not available in cache memory, then it referred as cache miss. Sorry, C-A-C-H-E, cache miss. Okay, so whenever the processor finds some address code data, so that data is not available in the cache, it wants to execute some operation, but that is not present in the cache, so then you call it as a cache miss. Cache miss. So if the desired memory block is then what it does, then what the processor will do if the data is not present in the cache, then the desired memory block, whatever the processor want, that block is copied from main memory into cache using the cache control and sent to the CPU. Okay, so if the processor finds something, if the processor wants some data, if that is not present in the cache, it referred to as a cache miss. Whenever the cache miss is occurred, the processor, the desired memory block is copied from main memory from main memory to cache, from cache to CPU. Okay, so this is how the data will be transferred. CPU, cache, main memory. Okay, so the data transfer will be taken from cache to CPU and from main memory to cache. So this is how the operations are, the data is transferring. So here you call it as a block transfer. So block will be transferred at a time from main memory to cache. From cache to CPU, only word will be transferred. Word transfer. So here the transfer of bits will be word transfer, where here will be the block transfer. So this is about the cache memory. So let me explain the formula for the hit ratio. Hit ratio of the cache. So here the hit rate is equal to number of hits by total number of bus cycles into 100%. So this is the formula to calculate the hit rate. So what is this hit rate? Actually, this hit rate is used to calculate the number of hits. Number of hits nothing but success in finding the words in cache. So number of hits, you call it as a success in finding the number of words in cache. Suppose the processor is asking the CPU whether the data is present or not, whatever it requires. Suppose if the data is not present, that is, you call it as a miss. If the data is present, then it is success. So this number of hits indicate the success in finding the number of words in cache by total number of bus cycles. Bus cycles means total CPU reference to memory. So reference to memory means total number of hits plus miss, total everything miss and hits done by the CPU. The CPU, how many times it is asking, everything information, you call it as total number of bus cycles. So number of hits by total number of bus cycles into 100%, you call it, you can calculate the hit ratio. Okay, so this is about the cache memory. Thank you.
So do you understand the concept of the video while you're watching the video? So it explains the cache in simple words.
Yeah, got it.
Okay, so let's talk about the effectiveness. So effectiveness of the cache mechanism is based on the property of computer programs called locality of the reference. Also, analysis of program display the most of their execution time is spent on routine. So in which many instructions are executed repeatedly. So routine means many instructions are executed again and again, repeatedly, time to time. So analysis of the program displayed that most of their execution time is spent on the routines. So routines requires more time. This instruction may constitute a simple loop, nested loop, and few procedures that repeatedly call each other. So do you know about the loop? What does it mean, loop?
Loop, it's like function that keeps on repeating until some kind of condition is true.
Yes.
False. When the condition is true, it'll keep on doing it, and when it becomes false, it'll stop.
So it means that one process, one execution repeats again and again until the certain time, certain condition is fulfilled. So we have simple loop, we have nested loop, and few procedures that repeatedly call each other, which means that simple loop can call nested loop. A nested loop can call the few procedures. So like this, each system is kind of connected to the other system. Then memory instruction in localized areas of the program are executed repeatedly during the some time period, and the remainder of the program is accessed relatively infrequently. So this is referred to the locality of the reference. Let's talk about temporal and spatial localities. So I will skip this part for you. Okay, temporal and spatial localities is these two concepts you have to read in your free time. And if you have any question, you can raise your question in the next lecture.
Okay.
Then we have cache memory organization, like why we use usage of the cache memory. So consider the simple arrangements shown below. So we have processor, we have cache, and we have main memory. Yes, but each three component is connected each other. Yes, processor connected to the cache, cache connected to the main memory. So like this, you can know the main like organization, main architecture of the cache memory. Usually memory, cache memory, serve reasonable number of blocks. So, but this number is small when you compare the total number of blocks in the main memory. So the blocks, the number of blocks is smaller when you compare the number of the blocks in main memory. So cache memory store the smaller number of the blocks rather than main memory. So correspondence between the main memory blocks and the DOS in cache is specified by mapping function. So let's talk about cache replacement algorithm. When the cache is full and memory word that is not in the cache is referenced, the cache control hardware must decide which block should be removed to create space for the new block that contains the reference word. So cache control hardware, we have the term which is cache control hardware has to decide which block should be removed when we have problem. What kind of problem? Problem is when cache is full and memory word that's not in the cache is referenced. So in this case, control hardware has to decide which block should be removed in order to create space for the new block. So the collection of the rules for making this decision consists the replacement of algorithm. So we need the algorithm in order to collect a collection of rules for making the decision. But let's talk about the cache more deeply. So let me show you. Let me show you the video. Then we will continue again, okay?
Okay.
Hey friends, welcome to the YouTube channel all about electronics. So in this video we'll understand what is cache memory in computers and the laptops. So in this video we'll see what is the importance of this cache memory, what is the typical size of this cache memory and what are the different levels of cache memory that you find inside the computers. So before we understand this cache memory, let us see different kinds of memory that we see inside our computers. So the first kind of memory that we find inside our computers is the non-volatile kind of memory, like a hard disk drive. So this hard disk drive contains a mechanically rotating fast disks, which is also known as a platters. And if you see any commercially available hard disk drive, the typical rotation speed of this disk is either 5400 or a 7200 RPM. So as this hard disk drive contains a mechanically rotating part, so in terms of the speed they are quite slow. So the typical read or write speed that you get with this hard disk drive is in the range of 80 to 150 megabytes per second. But if you see the clock speed of the CPU, it is in the range of 1 GHz up to the 4 GHz. So even though the processor is capable of accepting the data at much higher speed, but it cannot get the data through this hard disk drive at the same rate. And that is where the second kind of memory comes into the picture, that is a random access memory. Now this random access memory is faster compared to the hard disk drive. So this RAM can provide a data to the CPU at a much faster rate compared to the hard disk drive. But still it is slower than the clock speed of the CPU. So the typical speed of the RAM is in the range of 400 MHz up to the 800 MHz. Still it is lower than the clock speed of the CPU. But if you see the newer generation of the RAMs like DDR3 and DDR4, then they can operate at a much faster rate like 1600 MHz or up to the 2100 MHz. So now if you see the speed of these RAMs, they are comparable to the clock speed of the CPU. So now you may say that these newer versions of RAM can supply data to the CPU at the rate at which they want. But the answer is no. So the modern day processors which we are using are not a single core processor, but they are multi-core processors. So this processor could be either dual core, quad core, or maybe even octa core. So if all the cores are asking for data at the same time, then this RAM cannot be able to deliver the data to all the cores at the same time. And that is where this cache memory comes into the picture. So this cache memory is fastest among all memories. So now this cache memory is also a random access memory, but it is a special kind of RAM, which is known as a static RAM. So unlike the dynamic RAM which we find inside the normal RAMs, the static RAM is quite fast. And the typical size of this cache memory is in the range of kilobytes up to the megabytes. So the data which is frequently required by the CPU can be supplied by this cache memory. So generally some instructions and some data which is required by the CPU is stored inside this cache memory. So now let us see the different levels of this cache memory. The first level of cache memory is known as a level 1 cache or a L1 cache. So in this level 1 cache, the tiny amount of memory is integrated inside the CPU itself. And all the cores inside the CPU have their individual level 1 cache. So as this level 1 cache is integrated inside the CPU, so they can operate at the same speed of the CPU. And that is the reason the level 1 cache is fastest among the all caches. Now the typical memory size of this level 1 cache is in the range of 2 kilobytes up to the 64 kilobyte. Now inside this level 1 cache there are two kind of caches. The one is instruction cache and the second is a data cache. So the instruction cache stores all the instructions which is required by the CPU, and the data cache stores the data which is required by the CPU. Now let us see the second level of cache. So this cache is known as either level 2 cache or a L2 cache. Now this level 2 cache could be either inside the CPU or it could be outside the CPU. Now this level 2 cache could be separate for all the cores or it could be shared between all the cores of the CPU. So if this level 2 cache is outside the CPU, then it is connected with a very high speed bus with the CPU. So the memory size of this level 2 cache is in the range of 256 kilobytes up to the 512 kilobytes. But in terms of the speed, they are slower than the L1 cache. Now the third kind of cache is known as a level 3 cache. So all the processors do not have this level 3 cache, but some higher end processors have this level 3 cache. And this level 3 cache is used to enhance the performance of this level 1 and level 2 caches. Now this level 3 cache is shared among all the cores and it is outside the CPU. So the memory size of this level 3 cache is in the range of 1 megabytes up to the 8 megabytes for a high-end processors. But it is slower than the L1 and L2 cache. But still it is faster than the random access memory or a RAM. So now let us see the process flow when CPU needs some data. So whenever CPU needs some data, then first of all it will look inside the L1 cache. So if it will not find inside the L1 cache, then it will look inside the L2 cache. And if the data is not inside the L2 cache, then it will look into the L3 cache. So if the CPU finds the data inside the cache memory, then it is known as a cache hit. But if data is not available inside the cache, then it is known as a cache miss. So suppose if data is not available inside the L3 cache, then the CPU will look inside the random access memory or a RAM. And still, if doesn't find any data inside the RAM, then it will get the data from the hard disk drive. So when you are starting your computer for the first time, or you are opening some application for the first time, then that data will not be available in either cache memory or in the RAM. So at that time the CPU will get the data from the hard disk drive. But once the application is open, and then after if it requires some data, then CPU will get the data either from RAM or through the cache memory. Now you may ask that if this cache memory is so fast, then why the size of this cache memory is only in the megabytes? So the reason is that this cache memory is much costlier than the other memories, and that is the reason you will find only a few megabytes of cache memory inside a CPU. So whenever you are buying some desktop or a laptop for yourself, don't only look the random access memory but also look the how much cache memory that CPU has, because this cache memory decides the overall performance of the processor. And the same thing is applicable for the smartphone processor as well. So I hope in this video you understood what is the cache memory and what is the significance of cache memory inside the computers. So if you have any question or suggestion, please let me know in the comment section below. If you like this video,
So it's all about the cache memory. Do you have any question?
No, not really. It's clear.
Okay, let's talk about the cost effectiveness. To be cost effective and to enable efficient use of the data, cache must be relatively small. So in order to win in terms of the cost and uh, in terms of efficiency of data, cache has to be very small. So, but cache have proven themselves in many areas of computing because typical computer application access data with a high degree of locality of reference. Such access pattern exhibit, which means display temporal locality, where data is requested that um, has been recently requested already, and spatial locality where data is requested that is stored physically close to the data that has already been requested. So let's talk about the computer memory system overview. So the complex subject of computer memory is made more manageable if we classify memory system according to their key characteristics. The most important of these are listed in table. Please look at the table. We have the location, capacity, unit of transfer, access method, performance, physical type, physical characteristics, and organization. So in location, we have two types of location, internal and external. When it comes to capacity, we have number of words and number of bytes, yes. When it comes to unit of transfer, so we have word, word, either in block. And we have access method. So we have four component access method. First is sequential, direct, random, and associated. So then we have performance, access time, cycle time, transfer rate. Then we have physical type, semiconductor, magnetic, optical, and magnetic optical. Like this, we have two types of physical characteristics, like volatile and erasable, non-volatile and non-erasable. So the term location refers to whether memory is internal and external to the computer. Internal memory is often equated with the main memory. So, but there are other forms of internal memory. The processor requires its own local memory and the form of registers. Then the control unit portion of the processor may also require its own internal memory. We will defer discussion of this later two types of internal memory in next class. So
Okay.
typically, for internal memory, expressed in terms of bytes. So 1 byte equal to 8 bits, or we call words. So common word lengths are 8, 16, and 32 bits. External memory capacity is typically expressed in terms of bytes. Okay, so let's talk about unit of transfer. Okay, we will not talk more about unit of transfer, but I will try to explain you how to say most necessary part. So normally the size of the word is typically equal to the number of bits in order to represent integer and instruction lengths. So, but there are many exceptions. For example, C90 has 64-bit word lengths, but use 46-bit integer representation. But when it comes to Intel X 86 architecture has like a wide variety of instruction lengths expressed as multiples of bytes and word size of 32 bits. Then we have addressable units. So then we have unit of transfer. So in some system, addressable unit is a word, but many systems allow addressing at the byte level. In any case, the relationship between the lengths in bits of address and number n of addressable unit is 2a equal to n. For main memory, this is the number of bits read out of or written into memory at the time. Okay, so method of accessing. So let's talk about the method of accessing more deeply. We have two types of method of accessing. First one is sequential, second one is direct access. So when it comes to sequential access, memory normally is organized into units of data. For example, let's call it records. So access has to be made in specific line of sequence. It's stored in addressing information is used to separate records and assists in the retrieval process. Then we have direct access. Like a sequential access, direct access involves shared read-write mechanism, yes. But individual blocks or records have unique address based on the physical location. Access is accomplished by direct access to reach general vicinity, plus sequential searching. Then we have random access, then we have associative. So in random access, each addressable location in memory has unique, physically divided in addressing mechanism. The time to access given location is independent of the sequence of prior access and is constant. Therefore, any location can be selected at random and directly addressed and accessed. And associative. This is a random access type of memory that enables the one to make comparison of desired bit location. Word is therefore word is retrieved based on the portion of its contents rather than its address. As with ordinary random access memory, each location has its own addressing mechanism, and the retrieval time is constant independent of location or prior access pattern. So before talking about the performance, let me show you short video. let's watch. Okay, so
When you think of memory in your computer, you might think of things like DDR modules, VRAM on your graphics card, or most likely just hard. When you think of memory in your computer, you might think of things like DDR modules, VRAM on your graphics card, or most likely just hard drives and SSDs. But there's actually another type of memory that's incredibly fast and essential to the speed that we've gotten accustomed to with modern computers. I'm talking about your CPU cache. No, not the money that you blew on that processor with hyperthreading that you didn't really need. What we're talking about is cache with an E. It's a specialized type of memory that's built into your CPU. But why the heck would your processor need its own memory? Aren't the 16 gigs of RAM or whatever the heck you already have in your computer good enough? Well, not really, to be honest. You see, those RAM modules are a heck of a lot faster than, say, a hard drive in terms of data transfer, like a lot faster. But your CPU actually wants data much faster than your RAM can even provide it. And on top of that, as CPUs have gotten faster over the years, they continue to outstrip typical RAM modules by wider and wider margins, meaning that without faster memory, your CPU is going to be sitting around doing nothing, like a kind of unproductive employee as it waits for RAM, and you'll run into bottlenecks as a result. This is where cache comes in. Unlike system memory, which consists of dynamic RAM or DRAM, your CPU cache is static RAM or SRAM, which is more expensive and takes up more space, but is much faster than DRAM because it doesn't have to be constantly refreshed in order to hold data the way that DRAM has to be. An average CPU will only have a few megabytes of cache, but it makes a tremendous use of this small amount of memory. You see, when a CPU accesses something from your main system RAM, it generally stores it in its cache, then uses complex algorithms to guess as to what other instructions or data it might need next. And it fetches those from your system RAM as well. Since these guesses aren't perfect, CPUs suffer from things called cache misses, where it searches its own cache, can't find what it needs, and has to access your system memory directly instead, which slows things down. Fortunately, however, modern processors have gotten pretty good at deciding what to put inside their caches, as they'll typically have a cache hit rate of better than 80%, meaning that most of the time your CPU is only processing what it finds in cache and doesn't have to bother talking to your slower system memory at all. And as you may have guessed, more cache is advantageous. So when you're shopping for a processor, the product page will indicate how much level 3 or L3 cache is built in, with higher end modules having a few extra megabytes. And if you're wondering what the heck happened to levels 1 and 2, these are smaller, even faster parts of the cache that your CPU will try and hit before looking for data in your level 3 cache. Okay, Luke, that's cool and all, but will better cache actually give me more FPS in games or faster speeds in my other stuff? Well, this can depend on the specific application, but you can see performance increases kind of overall on CPUs with larger caches. Fortunately, though, if you're buying a higher-end processor because you need more cores, higher IPCs, or better overclocking potential in general, it'll probably come with more cache as well. So it's not really something that you have to really think about too much. Of course, if you really want that high-end silicon, make sure that you're paying attention to how much cache with an S that your wallet has left. Are you trying to program payments into your app and it's just not that easy? If you're building a mobile app and searching for a simple payment solution, check out Braintree. Braintree's V.0 SDK is one amazingly simple integration away from giving you simple payments every time. Developers around the world have embraced the Braintree V.0 SDK as the easiest way to add secure mobile payments to their apps and websites. Once integrated, Braintree supports a bunch of different ways to pay, like Apple Pay, Android Pay, PayPal, Venmo, credit cards, and even Bitcoin. And if something new pops up, Braintree will support that too. It's used by Uber, Airbnb, GitHub. It's scalable. It integrates into your app easily, just a few lines of code. Try it in the sandbox. Learn more about Braintree in the video description down below, and get your first 50,000 in transactions fee-free at braintreepayments.com/techquickie. But are you cashed out? If you are, be sure to like the video, dislike the video, subscribe, do all those fun things. Then on your way out the door, be sure to check out Channel Superfund right across the street. They're fantastic, highly recommended. And as always, leave a comment on the little book as you leave with the suggestions that you might have for how we could make your stay even
So let's talk about performance. So what do you understand if someone talk about performance? What does mean performance?
Means like probably maybe the quality of the process, or I mean quality is like the time that it takes to do a certain operation, or yeah, well, that's what I understand as performance.
Anything else?
Not really sure.
When we talk about performance, so it has it works. The mark for your work as a kind of like someone is give the rank for your work performance. Okay. In terms of the performance, we have two types of performance. One is access time. Second one is memory cycle time. So for random access memory, this is the time it takes to perform a read or write operation. That is the time from the instant that address is presented to the memory to the instant that data have been stored or made available for use. For non-random access memory, access time is the time it takes to position the read-write mechanism at desired location. Okay, when it comes to memory cycle time, the concept is primarily applied to random access memory and consists of access time plus any additional time required before second access can commence. But you have to note that memory cycle time is concerned with the system bus, not the processor. So let's talk about the performance in detail. So here we have transferred rate. This is a rate at which data can be transferred into or out of memory unit for random access memory. So it's equal to 1 over cycle time. For non-random access memory, the following relationship is half. So it is a formula. So T equal to like a Tn is average time to read or write n bits. TA is average access time. N is number of bits. Okay, and R is transfer rate in bits per second. And
Okay.
you have to learn this formula. So we have physical types. Variety of physical types of memory have been employed. The most common today are semiconductor memory, magnetic surface memory, and used for disk and type, and optical and magneto-optical. So in terms of physical characteristics and organization, several physical characteristics of data storage are important. In volatile memory, information decays naturally or is lost when electrical power is switched off. When it comes to magnetic surface memories are non-volatile. Semiconductor memory may be either volatile or non-volatile. Then we have for random access memory, the organization is a key design issue. In this context, organization refers to the physical arrangement of bits to form the words. The obvious arrangement is not always used. So let's talk about memory hierarchy. before talking about this, okay, so what does mean hierarchy?
I'm not sure.
It's a kind of scheme, kind of structure, kind of block diagram, which displays the architecture of the memory. Okay, the design constraints on a computer's memory can sum it up by three questions: how much, how fast, and how expensive. The question of how much is somewhat open-ended. If the capacity is zero, applications will likely be developed to use it. The question of how fast is, in a sense, easy to answer. In order to achieve great performance, the memory must be able to keep up with the processor. Okay. Okay, let's talk about memory hierarchy. So we have L0, L1, L3, L2, L3, L4, L5, L6. Yes. According to hierarchy, we have registers in L1. Sorry, L0. L1 cache is situated in L1. L2 SRAM is situated in L2. L3 cache is SRAM also, is situated in L3. Then we have main memory in L4, local secondary storage L5, remote secondary storage L6. Okay. So from the top to the bottom, larger, slower, and cheaper. From the bottom to the top, it's smaller, faster, and costly. Okay, caching in the memory hierarchy. So in general, cache is a small, fast storage device that acts as staging area for the data object stored in a larger, slower device. The process of using a cache is known as caching. The basic principle of caching in memory hierarchy is as follows. So please pay attention for the cache hierarchy. Here we have level. So we have two components. So we have cells, and we have communication between the levels, the steps of levels. When you see the picture, so data is copied between the levels in block size and transfer units. So data can be transferred from the level to level in block size transfer units. Okay, so let's talk about cache hits. When program needs particular data objects D from level K plus 1, it first looks for D in one of the blocks currently stored at level K. If D happens to be cached at level K, then we have what is called cache hit. The program reads off directly from level K, which by the nature of the memory hierarchy is faster than reading D from level K plus 1. Yes, for instance, program with a good temporal locality might read data object from block 14, which is result in a cache hit from level K. When we say cache miss, say like 1 minute. So when you say cache miss, the data object D is not cached at level K. Then we have what's called cache miss. When data object is not cached at level K, so in this case we may occur cache miss. When there is a miss cache at level k fetches the block containing D from the cache at level k plus 1. Possible overwriting existing block if the level k cache is already full. This process of overwriting existing block is known as replacing or evicting the block. The block that's evicted is sometimes referred to victim block. Okay, let's talk about the types of cache miss. It's sometimes helpful to distinguish between different kinds of cache miss. So we have compulsory miss, all called miss, conflict miss, and capacity miss. Conflict means which the cache is large enough to hold the reference data objects, but because they map to the same cache block. Capacity means when the cache is just too small to handle this particular working set. Okay, let me show you modern computer system, ubiquity of coding. So we have type and we have cached and where it's cached and latency and managed by. So it's stable for you in order to learn in your free time. Okay, do you have any question about today's topic?
I think no. Everything was clear about the cache.
Okay. So I noticed that in previous lecture about the lecture that is held in tomorrow on Sunday. But Sunday we will not have any lecture because it's day off and because we shifted to Sunday's lecture today. Okay.
Okay.
So
Yeah.
next class will be held next week.
Okay.
Okay.
Yeah.
Okay. So
Yeah,
if you don't have any question, so have a nice day.
Thank you.
Take care of
You too.
yourself. Okay.
Yep. Bye.
Bye.